Welcome to this session about checkpointing, which will be presented by Olivier Matelas from UC Louvain. Okay, Olivier, the floor is yours.
So, hello everyone. So, welcome to this session about checkpointing. So, of course, the first question here is, what is checkpointing? I guess if you attend the sessions, you might have a guess at least. So just take a simple example, a simple program. Just for the name of the executable, you can guess what it's doing. It's just counting, obviously. So 1, 2, 3, and so on. And then, of course, at some point, you're bored by this stupid program and you hit Control-C, so you cancel the program, it stops. And if later you restart the program, what's typically going to happen is that the program restarts from scratch. So it restarts to start from 1 and continue up to the end of the program so that you are bored again and hit Control-C again. So that's what we call without checkpointing. It means that each time you start your program, you restart it from scratch. What we want to be able to do, that you will be able to do at the end of this lecture, is transform this program for this behavior restarting from scratch to this behavior, be able to restart nearly where you have stopped it. Not exactly where you stopped some of the times, but nearly where you have stopped. So that's the main point of these lectures today, is to tell you how you will be able to do that, either in your own program or the program made by someone else. Then, of course, that let me continue. So checkpointing is really saving a computation so that it can be started, resumed later, and not restarting from scratch. So more in detail, what we are going to cover today is first some general concept about checkpointing, a lot of definitions. Then something which is partially related to checkpointing, but it's actually much more general, is what is signals. So we are going to cover what a signal is and how we can use it in the context of checkpointing. Then we will, in some sense, continue dive a bit more in the session of this morning. So with Slurm, how can we use Slurm for checkpointing? So that's, of course, very important in the context of a cluster. And the last part of this lecture is about a program called DMTCP. What a crazy name. And the idea of this program is to transform a code which is not checkpointable by design to a code which will be checkpointable. So take any code that you can think that you use every day that has no checkpointing at all. DMTCP will allow you to convert that code into something checkpointable. So the first question is, of course, okay, who cares about restarting from scratch? And in some cases, you are true. I mean, for the counting 1, 2, 3, if I cancel after 3 seconds, you don't care. Restarting is as good, it's probably even better in a lot of cases. Now, if you take a text editor, for example, a lot of you have maybe already started to write a thesis or just starting a thesis, like a master thesis last year or whatever. At some point, you need to write some big reports. And of course, each time you quit your editor, you don't want to restart from scratch. So there is certainly a lot of places, a lot of situations where being able to save the state of your computations, to save your work is, of course, really important. Not only when you write text, obviously, but also when you have those very long computations that takes 15 days. And then at some point, for whatever reason, you need to stop that computations because you change laptop or whatever reason, right? That's also important to not lose your computations in the middle. So the main idea is you want to be able to save the program state. What I mean by state is really all the variables, all the content that really define what your program is, what is the current status of your program. That's anything that you need, number, what are the files which are open, what is the content on some files. I mean, you typically know what your program is doing, and that's are the information that are needed. You don't want to do that at time, basically. You want to do that at a regular point. Regular means what it means, but it's every time what we call a checkpoint is a counter. So it can be every 5 seconds. That's then you say, okay, every 5 seconds, I'm going to save my state. That's what we call a checkpoint. It can be also every iteration. So if your program has multiple iterations, that stuff that's repeat or a big for loop, you can say each time I'm starting or finishing my for loop, I'm going to save my state. Or it can be if something happens, if someone tell me, oh, save your state now, that's why you need to do it. So that's the typical solutions. When something happens, that's what we use later. That's what we call a signal. That means it's a reactive way to do it. And then the point, of course, of saving that state is being able to restart from there. So being able to save that situation. So whatever happens when that state is saved, you are able to restart from that situation, obviously, instead of restarting from scratch. So in the context of high-performance computing, in context of cluster, there are mainly 4 reasons why you want to use checkpointing. And the first one is to be able to fit in time constraint. Damien explained this morning that in each cluster, we have a hold time. So that means you are not allowed to run 2 long jobs. If I take Louant 3, we have 2 queues in that case. We have the normal one and the debug one. On the debug one, we have, you are allowed to run jobs of maximum 6 hours. On the normal one, you have a maximum of 2 days. And on some of the clusters, it go up to 20 days, if I remember correctly. So it's sometimes difficult. It can be sometimes difficult to be able to fit your program during those time limits. If your program runs for a month, good luck with that. But if it's running for a month, you will still need to use those clusters. So you need to have a way to fit it inside. And it's, of course, important that you use those hold time, because those hold time are also in place for you. Having small hold time allow basically to have a user who just arrived on the cluster and want to run a small jobs will have a much faster access to the machine if basically the hold time is small. Because if you have hold time of 3 months, let's say, you might have to wait up to 3 months to have 1 machine available for you because everyone has blocked the cluster for 3 months. So that's not a good idea for the user, to my point of view, to have hold time very, very long. Of course, if the hold time is too short, anyone needs to do checkpointing all the time, and that, of course, a bit of pain. But typically, the best thing is to have relatively small hold time. And that makes the cluster much more reactive, because then it's much more easy for someone to start a computation. So if someone has very long jobs, then someone can enter in the computation. So that's why having a small hold time, but being able to checkpoint is really the best situations. The second reason why you can be interested on checkpointing is also monitoring your code, so that you have a file or database or whatever, where you have the information about what is the status of your code. And if you look at that file, you know what is going on. You will be able, since in principle you can restart from there, you should be able, if you know what your program is doing, obviously, you should be able to understand what is going on. And you can see, oh, no, there is something now, it's going in the wrong directions. I can maybe revert 1 or 2 iterations or whatever. So you can able to monitor, or if you need to debug something that happens after the 25 iterations, at each iteration takes 3 hours, you don't want, when you do debugging, to rerun all the iterations. You might only want to rerun the last iteration. So that's also can be very useful for debugging, to not having to restart everything from scratch, restart from the last save point, and then from there you can run multiple times to try to understand what's going on in your code, adding a lot of print statement to be able to pinpoint where your issue is. So a less good issue in some sense, at least less good in our side, you might also have on cluster, you might also have computer that crash for whatever reason, hard disk failure, a power cut, name it basically. There is always a reason why something's can go wrong. On whatever reason, we have a lot of machines. We try to avoid that as much as possible, obviously, but this can happen. And if you run a code for, let's say, 15 days, and I know code that's running for that long, then you are always tributary if that the machine will be able to continue that long, will be sustained the charge for 15 days, or will you fail at some point due to whatever reason. And of course, the longer your job is, the higher the probability you have to have a problem, and the more impactful it is if you cannot recover from it. So the last reason is what we call job preemption. So that's something we don't actually use in the CSC, at least so far, is the possibility for high priority jobs to pause a low priority job so that it can be scheduled quicker. So that's something we are not using. It's used on some clusters. It's quite useful also to balance and have the fair share on the cluster, but that means also that we put a lot of pressure on all the code to be checkpointable. So that's something we're not using, but some cluster can. Okay, so the first question, of course, is there basically two types of usage of checkpointing and two types of how you use the cluster actually. So either you are a developer, which means you are creating your own program, and in that case, I will discuss that a bit more in details later, but in that case, it's your duty in some sense. It's your choice also, you are not forced to do it, but it's your duty to propose checkpointing in your code. So in that case, you have full control on how to adapt your code to make some pointing. On the other side, you can also be a simple user of a program, that someone else that's have developed the programs or not. So in that case, what you need to do is to basically check the documentations. A lot of common code have checkpointing available, and probably a bit less common code, or even some common code as well, might not have checkpointing available in the program. So in that case, what you need to do as a user is going to get documentations to their website, to their paper, and check, do that program has checkpointing or not? And then you read the documentations, you need, okay, I need to put that flag when I run the program or whatever, and you are able to learn how to do it. And I take here two examples. One is Gaussians, and if you look at the FAQ, there is one question which is not called checkpointing, but it's the same. How can I restart a job that was interrupted? That's the same idea of checkpointing. So they will not always use the word checkpoint, obviously. Sometimes they will use the word restart. That's the same here for CPQK, which is also, there's a page with restarting. Even if they say that this text is probably out of date. So check on CP2K how you can do it if you need that program, obviously. So now let's, so if you're a user, the last part of this lecture is also about how you can convert non-checkpointable programs, so a program that doesn't have that feature built in, how you can anyway use checkpointing. So we'll cover that at the end. So now I will focus a bit more how you can do it as a developer. And there are typically a couple of questions that you need to ask yourself when you are going to implement inside your code the checkpointing. Is, of course, how much is going to cost you. That's what I call here I/O overhead. So how much time does it take to save the state? And how often do you want that state to be saved? I mean, that's, of course, the less often you save the state, I mean, it's less useful, because that means you don't, I mean, you have less reactivity, obviously. But of course, you don't want that your code is basically spending 50% of its time saving its state and 50% of its time making the computations. So that's also one thing you need to think about, is how easy it should be for the user. And that's, of course, the answer is typically it should be very easy, but it's not always very simple to do that. And then the last question, which is often not taken into account, is what is called portability. So do you want the user to be able to run on a machine, then stop the computations on that machine, move the state to another machine, and being able to restart or not? So quite often, of course, that creates a lot of issue, because some dynamic library might not be existing anymore, some files might not be there. I mean, there is a lot of assumptions hypotheses on how that could work if you want to be able to move from one machine to another, obviously. So that's something which is quite often not handled. And as a starting point, of course, you might just think, okay, no, let's do everything on the single machine, and that's much more easy. But if you want to be generic, that's the question you need to ask yourself. Do you want to support the fact to pass from one machine to the other? So here is a couple of questions that is worth thinking at the beginning. How much do I need to write code in order to support that? I said portability. Can I stop on one machine, restart on another? how much memory does it require, disk space in that case, and how many computation does it require as well. So the typical stuff, and I will start my first demonstrations. The typical stuff is to save basically at each iteration, and that's a very simple example I will show you, which is you will all be able to figure it yourself. So if you go on the Indico page, you will see the PDF. Then you will see here all language example. So that's a very old table done by Damien, which contains example. I will only present during the presentations everything in Python, but there's also example here in MATLAB, in R, in C, in Fortran. So all what I've presented is obviously applicable to basically any language. And there here you have all those examples, because the syntax is of course slightly different for all those examples. And you have all examples here. All the files that I'm going to use in the presentation is in the second table, checkpointing.tgz, and that's where I have all the files that I'm going to use in this presentation. Okay, let's go back to my presentations. So here I open a shell. I'm already on the Lemaitre tree, and I'm not sure where I am on Lemaitre tree. So in my home, so I need to move to the directory where all those files are. Okay, so this example is a bit too complex, I would say, for what it needs to be. I mean, especially those lines here are not really important itself. One thing I will always fight in these lectures, in all the examples, I will fight against buffering. So I always want to be able to have any printing, any information printed into a file, especially, to be directly written on disk. So there is a lot of tricks that I'm using just to avoid that Python is buffering. So when I say write in a file, actually not writing in the file right now, but in a couple of seconds, or in Slurm, that's the same. They also have buffer. And all those buffers, of course, are important overall for performance in general. But here, in order to be able to have a relatively reactive presentations, it's important that I kill as much as possible all those bufferings. And I'm not sure I've killed all of them. I still have some. But that's why you have some line of code which are a bit not that clear. And then you see here this import CT types. That's something I'm typically never use in my Python programming. And that's only there to try to avoid those buffering, actually. So what I'm doing, so this script is only doing the program I showed you at the beginning of these lectures. Is just doing to print number one after the other, print 1, print 2, print 3, and so on. So what I want to do here is that at each iteration, I'm going to save the state. So in that case, the state is just what is the last number I've written. So that's if I'm stopping that program and restart, I will be able to restart at that number. So my state here is saving a file, and that the file is named state. So that is where I'm reading. So when I start my program, the first thing I'm doing, I'm checking if there is a state file. If that file exists, then I'm reading that file, and I'm saying I'm going to start my numbering, my iterations at that value. Otherwise, if that file doesn't exist, or if it is corrupted in any way, then I'm starting to count at 1. And then I'm going to stop at 500, and then I'm looping. If you don't know Python, that's for I in range. Range means we are going to count from start to stop by step of 1. I'm printing it on the screen. This is Python 2 syntax. And then after I've printed it, then I'm writing into the file state again, what is the value? And I'm putting I plus 1 so that everything is nice. It doesn't matter too much, obviously. And then again, I have those 2 lines, which are just to avoid buffering as much as possible, that you don't care too much. And then I'm telling my code to sleep a bit, otherwise everything is printed too fast, obviously. And I'm basically counting seconds, so I'm printing a number, waiting for a second, then I'm printing the next number, and so on and so on. So I'm going to execute that. So it's count.py. So as I said, I'm just printing number. I'm going to quit here. And now if you're looking in the directory, you can see that this file was created. It was created just now at 2:21, already 20 minutes passed. So if I'm looking inside that file, I will see a number which is 26, but you see that this number will be overwritten very soon. So I'm reopening now. Now it's already 31. So that's really saving the status. Now I can kill it here. It will save, I guess, 36. Yes. And now I can restart my program, and it restarts at 36 exactly. So this is the most simple way to do checkpointing, obviously. I guess you are all bored because that's nothing really new for you so far. Yeah. So let's try to do something a bit better. So instead of saving the iterations at each iterations, let's try to do it when it's useful. And when it's useful in the previous case, you don't care to save the state every second. What you really care is, oh, I'm quitting the program now because I'm doing Control-C, so I'm killing my program. That's the time where it's interesting to save and all the other ones are basically a waste of CPU time and I/O access. So how do you do that? How do you treat that information? Oh, my program is going to be killed now, actually. And in Unix, any processes can receive signals. And you're already using probably, and actually I already did in front of you, to use signal. So signal can be used by the user, and you are doing that probably a bit every day. I mean, if you know a bit Linux. But what I did in front of you was to kill my program with Control-C. And that's a signal which is called sigint, which has a number 2. And that's an information that the program receives. They say, oh, the user wants me to quit. There is other signal you probably, I mean, it's a bit less common, Control-D, for basically when you have interactive sessions, to say, quit these interactive sessions. One program which is I used for years, so I guess a lot of you know as well, is Control-Z, that allow you to make a program to sleep. So it's going to pause, and then typically you have other signals, FG and BG, to restart the program, either in the background with BG or in the foreground with FG. You also have the kill command that can send signal. So if you use kill command, that's by default is the signal number 15 called sigterm, and that's also a code to kill your program, or you have the highest level of kill -9, which send a sig kill. So you have plenty of type of signal that you don't need to know all the name and stuff like that. That's not important. But you have plenty of signal that you can send, but also the OS can send the signal. And for example, you will send a signal segmentation fault. No, that's not possible. You are reading memory that is not available. Or something else is broken. That also will be a signal. And to all those signals, there are typically what we call a default actions. So that's if you don't code your program in a specific way to recover, something will happen. And that can be just, okay, don't care, continue as normal. And that's what we call ignore. Or in most of the case, that means you are going to quit your program. Actually play a bit with that. And that's exactly what we are going to do in the second demonstration, is to be able to, when there is a Control-C, catch the information, oh, someone's trying to kill a signal, kill your program with the control. Let's take that information, let's take that signal, and let's do something. And that do something means that you can continue your program if you want, but typically what you want when you have a Control-C, that means you save the information, you make your checkpoint at that time, and then you quit. Because you typically, when the user do Control-C, you want to allow the user to stop the program, obviously, but you want to save the state, obviously, at that time. And that's the idea. So let's go to this second file. We'll do it here as well. So that's where the tarball with all the different different language is, of course, very important, because all the way you take and catch the signal is always slightly different. But the idea is globally always the same. So what you need to do is to define a functions. Functions, in this case in Python, the number of parameters that can change. In a way, typically you don't use this parameter. Signum is the number, obviously, in the frame if you have multiple frames. So that's a function that you want to be executed when the user is going to hit Control-C. In order to tell your code that's when you want to have that functions, you typically have a library. In the case of Python, it's a signal, where you say, okay, when you have a sigint, if you remember, that's when happening, the signal that's happening when you hit Control-C. When the user hit Control-C, then execute that function signal handler. And of course, for all different languages, the syntax is of course a bit different, but conceptually, that's the information that you will give to the code. If you receive that message, then do these custom actions, which in this case is calling signal handler. So here, what I've done in these functions is just modify a global variable. So we have a global variables interrupted, which is by default set on false, means the programs should continue. But if suddenly this the user hit Control-C, what I'm doing is changing that global variables from false to true. The rest of my program is basically the same. The only difference now is that if my code is interrupted, so if I suddenly this value interrupted pass to true, then I'm stopping my code, I'm stopping my iterations, and then now I'm saving my state not inside my for loop, but outside my for loops. And there's two cases where I can go out of the for loops, either because the user hit Control-C, that puts interrupted to true, or when everything is finished, then in that case it's maybe a bit of waste, but okay. It's telling that the work is finished. And then one thing which is not that crucial for this example, but it's useful in general. Since I'm quitting with Control-C, I'm returning my programs. I don't want it to return with the number 0, which is the default saying, oh, my programs ends correctly. I'm going to end it with the value 1, saying, oh, there was an error in my program. It didn't end correctly. And that's always useful when you want to change program to know that, okay, that program was interrupted for whatever reason. So I'm going to run it here. So what I will do, I will first remove the state, so the state file. So I will restart at 1 again. How do I call it? It's count signal. So I restart at 1. And now, as you can see, the file state is not created anymore. So it's not as before where it was every second that file was overwritten. Now it's not there. And if I'm doing Control-C, that's exactly at that time that is going to happen. So now if I'm doing ls, you see that the file state appear exactly when I'm doing Control-C. So you have, of course, a small lag up to 1 second, obviously, between the time you hit Control-C and the time your program will actually quit. And now if I'm restarting, now that I have that file, I can look at the value. It should be 21, I guess. Yes. Now if I'm restarting my program, you will see that I will restart from 21, obviously. So that's a much better way to do it, obviously, because I'm really saving my state only when needed, only basically when my program is quitting. Of course, there are also drawback. It means I don't know at each second what's going on, and you can potentially define more signals in order to be able to communicate. Okay. So that's very great, but you can ask me, okay, but how do I do that on the cluster? And how can I ensure on the cluster that basically I receive the signal that I want before my programs hit the wall time or something is happening? So there is an option. I don't think Damien mentioned it this morning, or maybe very briefly. I'm not fully sure. But there's a way, in any case, to communicate between different processes. And that is, it tells for sure that it tells me, oh, you have the scancel command, which is the equivalent on Slurm of the kill command. And in the kill command on your laptop, it's allow you to send the signal that you want. So all the signals I put on the screen before, all of them can be sent via a simple kill command to any process. And then you can do exactly the same with scancel. So if you say this command, scancel -l sig int, that's exactly the same as sending to a process on the cluster Control-C. It's exactly the same. Now, that's not very convenient, I would say, because that means you need to interact yourself and saying, oh, my job is going to eat the whole time. Quick, let's type scancel. Of course, that's not the way it should be done. So there is a very convenient options in Slurm, which is -- signal. And what this option is doing, it's allowing you to define the signal that you want to send to the process, and you can also define when. So the default is 60 seconds before the hold time. And since Slurm is always not very extremely precise, there is a tolerance, I would say. So when you ask 60 seconds, it can be between 2 minutes and 1 minute. So there's a 60-second, how to say, it's not precise as a second, but precise up to 60 seconds. So you have two options here. So you remember this morning, Damien was saying, oh, in your script, it's in your submission script, so it should be a bash script. And inside, it's better to put srun. So that's where you have this difference. So if you have srun inside your script, the signal will be sent to that particular instance, to that particular job. If you do -signal equal, and then you can put here the name or the number of the signal that you want to send. What you can also do is to send it directly to the bash script itself. And in that case, you need to prefix by B and colon. So that you have the two options how to catch it. So let's look at the example. That's exactly the same type of script that you have done this morning. So I put a job name options where I want to have my output. Here, something a bit different than usual. It's open mode equal append. So what I typically don't want is to overwrite each time the output. I want to have still the full log. So I tell that in the output, if the output already exists, just add the line at the end of it instead of, which is the default, overwrite it completely. So here, for example, of course, I took a quite small hold time, which is 3 minutes. Maybe on the cluster, actually, I even reduce it. And I'm asking Slurm to send me a Control-C signal to my program, which is in this case a very simple Python program, is the one I've shown you before, actually, to send it Control-C 1 minute before the hold time. That's what I'm asking. And so that my program, which is the same as the one I just showed you before, will receive that information. Oh, I received Control-C, and what we will do, it's simply going to save the state so that you will be able to resubmit the same script. And then here, it's really important, of course, that you have this srun here, because otherwise, if you just do Python, that's not what, it's not Python that is going to receive the signal. So let's go to the demonstration. Going here, oh, I didn't kill it, so let's kill it now. Let's remove the state again. Oops, sorry. Okay. And I'm going to relook at the file first before submitting so that you can see that it's basically the same file as the one I said before. I slightly decreased the hold time to 2 minutes 30. So that's because the problem, of course, of this lecture is that we are going to look at number growing all the time, and that's not very interesting. But I need to put some hold time, so we are going to wait around 2 minutes. And I'm already going to submit it so that it's already running. This stage. So. So you see it's already running, so that's good. I'm submitting on the debug partitions. It just said that it's typically quicker to start to run on the debug partitions. And otherwise, it's exactly what I said before in a srun command. The -u here is just to try to avoid buffering again, and then this is the same program as before. So the output will be in test.out. So now I can do tail -f test.out. And you will see that the program is doing what it does. So now we are basically going to wait around 1 minute 30 and 2 minutes 30. As I said before, Slurm is not extremely precise from timing. So when you ask him to send the signal 1 minute before, it can be up to 2 minutes before. So here I asked 2 minutes 30, so and I asked 60 seconds before. So okay, normally I should be able to maybe receive the signal at any time now. We'll see. So that's the annoying part that we have to wait. Let me check the questions. Oh, there are questions actually. The last two files are the same in the training website. Is this one or not? You mean on the Indico web page, I guess? I'm not sure about which file you are meaning. I see that Damien is answering a bit, but I'm not sure which file you are referring to. So the one I'm using for all the demonstrations are the one which is checkpointing.tgz, which is not the same as the other one, but they should not be the same in principle. If they are the same, I will double check. But one should be actually for all languages, and the last one should only be for Python. But I will check that after the lectures. And if you don't have the example for all the other languages like Bash, MATLAB, R, C, then I will make sure that it's also on the website, if that's your question. So here my job was canceled, obviously. So that's just because it's the whole time. So now I can check if I have indeed the state, and I have a state file. So now in principle, I can just resubmit it. So I'm resubmitting it. I'm also going to see that it's running. And now if everything is fine, this should restart. So here you see that I still have a small buffering that's related to Slurm actually. And they are common to try to avoid it. But it takes in a couple of seconds, if I remember correctly, 20 seconds before the next line is appearing on the file. So it's not important what I've used, but here I'm using watch, the command watch, in order to refresh the status of this command sq-u omat, so that I can see in real time what is the status of all my job on the cluster. And here on the left, I use tail -f to print the last line of the file, and that's also interactive. So each time a new line is coming into my file, I'm seeing it. So I'm really watching a file here, and here I'm redoing the same functions again and again on this side. So you see here that I've restarted. If I'm going up, I'm restarted from 1.05. I was stopping at 1.04, so that everything was perfect. Everything went on Slurm, was on Slurm. So now everything is on Slurm. So how do I kill that? So let me first quit my watch. Now, my job is still running. I want to kill it, so I will do scancel -u omat. That will kill all my jobs, which is of course quite dangerous to do. But in this case, I know that I have only one job, obviously. Okay, so that's the first of the demonstrations. I also have a second file. I will open it here, which is very, very similar. It's called submitsignal2.sh, which is actually exactly the same, but this part. So this is the only difference between this file. Also, maybe I put a full path to the script here. I'm not sure why I put that one actually. signal.py, yes. So what I do here is to automatically requeue my job. That's of course very interesting. So I'm checking the code output of this job. So if it finished correctly, it should return 0. If it did not finish correctly, it returned 1. And that's what I said before. Oh, here I'm ensuring that if my code was interrupted, it would receive the signal 1. And that's, of course, pretty important in this case, because I can then use this OR command, in some sense, to be able to say, execute this command if my previous job was not running correctly. And that's allow you to have a resubmissions completely automatically. So let's do that. Let's say the state. Submit. Now let me double check where my output is. I didn't check when I was putting my outputs. It's still test.out, so it should still appear here. And therefore I can just watch what is the status here. So now my job is running. As I said, there's a small buffer, so it will take a bit of time to basically restart here. The way I kill it, I'm probably going to restart from 105, actually, I guess. Because I didn't kill it with Control-C, I killed it with sig in, what was it, kill -9. Oh, no, actually, you say it? Oh, yeah, no, actually, yes. So actually, no, it's, I said something wrong. So it restarted 197, which is very good. I actually kill it with Control-C. I thought the default S cancel was not Control-C, but it looks like it is. So now basically I'm going to wait again that I'm eating the wall time for these jobs, which again, the wall time is 2 minutes 30 seconds. So it should happen very soon, especially because I'm sending the Control-C 1 minute before. And then what I expect to observe is that thanks to the single line I've added at the end, that this job is going to be requeued. So that's what we're going to observe. Just have to wait for everything to occur. So yes, you see, my job was killed here, but I still have a job here. So it was killed, makes sense. I hit my wall time, or a bit less than my wall time because of this Control-C. So that job is exit with the code 1. And then you see automatically I have now a new job, which is currently pending. And the reason why it's pending, it's called begin time. So when you have those automatic resubmissions, this requeue command, you are not allowed to restart the jobs directly. And that's to avoid with some kind of an infinite loop where your code is crashing directly, but requeuing itself, and then you are submitting like crazy again. And that would be, of course, very bad because that basically can overfill completely the cluster with a lot of jobs and will shut down the cluster. So to avoid that, you have to wait, I think, a couple of minutes before it restarts. But my job is here, and I will continue, but when I will go back, you will see that indeed it will be 309, 310. I could also wait. It's not extremely long time that I have to wait. But okay, I have 1, 2, or maybe 3 minutes that I have to wait in order to him to restart. I guess you can trust me now that indeed it will going to be resubmit. It's the same job, and then after that, it will recontinue from 309. Okay, this is another way to do the same stuff. I will not spend too much of time because otherwise I will be over time. But this is an example of how you do the same example, but without, I mean, in this case, I still use the srun in that case. But here you basically put the catch of the signal in bash. So you also define a bash function that's going, in that case, to the scancel and requeue. And then the way in bash that you say that's the functions you need to call when you have a signal. I do a trap. In this case, I'm sending another signal, which is not control C, but USR1, which means user one signal. But it's exactly the same as the example I showed before. We'll check my status. So you see now that my job was pending, it was automatically requeue, is now running. And again, because of the buffer, I don't see yet the number here, but they will appear, of course, relatively soon. And here they are actually, just at the point you see that they are printed and they didn't restart it from 0, obviously. And that, of course, will the requeue will occur multiple times in practice. So this I will skip because it's basically the same, and I'm running out of time. There's other way in Slurm in order to do that. I don't remember again that Damien explained that how to do that in Slurm. Is what we call job dependency. That's something very useful. I've used not really for checkpointing, but for other stuff. Like if you have workflow, actually, if you have a job, then other jobs, and then you have maybe even complex relation between your jobs. You need to wait that that job is finished before launching that one, and so on and so on. This dependency is very useful. So you can say, and what the command is the most useful for checkpointing, if that given job didn't finish correctly, then run this one. And that's allow you basically to be able to have checkpointing exactly in the same way as before, in a slightly more workflow way. But that's also a way you can play, I would say, and you can also schedule your code, is playing with those dependencies in Slurm, which is very useful. I've used some for something completely different, but that was very, very powerful. Okay, so this brings me to the last part of these presentations, which is slightly different. So here I'm not going to explain or to show you how you can modify your code in order to make it checkpointable. I'm going to use a program which is non-checkpointable by nature, not by nature, but so that program that was technically done by someone else that you are not allowed to modify for whatever reason, simply because you don't have the source or you don't are able to recompile it or whatever, and make it checkpointable. So for that, there is a program which is called DMTCP for distributed multi-threaded checkpointing. And that's very useful because it's doing these conversions. And basically what is doing, I guess, oversimplifying it a bit, is taking the RAM and it's basically dumping the RAM into a file so that you can restart the same amount of RAM. I mean, I'm probably oversimplifying what it's doing, but that should be at the end the same idea. So it's of course less efficient than just storing one number in the case of the checkpoint that we've done before, right? Because it's going to save the full program. So that's of course much more heavy. But what is nice with it is that you don't care about the language which is behind. You don't care about a lot of stuff, and you know that it's always going to work. So there's plenty of features. It's worked for MPI program, multi-threaded program. What is really important is this one. It's completely in the user space. So you don't need to have privilege. So you can run DMTCP for any program that you want. And that's, of course, very important. And you don't need to have permissions from us to doing that. It's completely transparent, which is also very important. That means you don't have to recompile your code. You don't need to have shenanigans. No, you just basically run the executable and that's it. So yeah, and one of the statement in the FAQ is if it's not working, it means that's a bug. So that's how a bit confident they are that it's basically very generic and then you can always use it. So we'll use again our simple program printing, except now that you see these versions. I put here the C versions. I'm going to use the Fortran one actually. What I'm going to do is to run that version. You see there is no state. I'm always starting at 1. I'm always finishing here at 10 or whatever number, but there is no file called state. There's no functions catching signal or whatever. That's the simple code that printing number one after the other. So the way it works is that you launch first your program and you launch it with DMTCP launch. So I'm going to the cluster. I'm going to cancel this, or it's close to finish actually. So I'm just going to cancel on this side. You see that it was resubmitting probably multiple times actually to reach 500. So you see that this requeue was actually working again, up to ending the end of my program, which was 500. So now my program is completely finished. So yes, what I wanted to do is now use a DMTCP, and I'm going to use DMTCP on what I call code orig program, which is exactly the same program I have showed you before in Python. Instead of my slide, it was in C. So if I'm typing what is on the slides, typing this, you will see DMTCP launch command not found. So this. So DMTCP is not a native program in some sense. It's a module. So I'm going to use a module. So I can do module spider DMTCP, as you should use to, as soon as you don't find something on the cluster, always use module spider DMTCP. I'm rebuilding the cache, and you see that you have two versions of DMTCP. One is in this release 2019B. This is the default on the method 3. It's 2.5.2. I prepare all my lectures with this one actually, so I'm going to use that one. But in principle, this one should be as good. So I'm going to change my release. And then I'm going to load this module. Okay. What's going on? It didn't like it. I release it 2000B and 2000A, and now it should work. Yes. So that is something that you should be used to. This module load is, of course, module spider, how to find programs available on the cluster, obviously. So now I have my programs. I can rerun the command here. I will do it. No, I will do all of them. So now I can launch my program like this. So now my program is running. Okay, maybe I should have, that should be okay, I guess. I just will not have the buffering. Maybe I should run the full command, that will be better. Okay, I have some small issue here, which I should not have run it on the terminal. Okay, so basically what it's saying, what the code is doing is you launch it like this. So you have DMTCP launch and then your program. And then what we call is coordinator. So in top of your program, there is another program, DMTCP, which is going to check your program. And then you can send in command. So if I'm looking at the full command here, DMTCP command, in that case, I'm asking for checkpointing, and then at some point, I'm asking to quit. So that's how you communicate. So doing that in the command line, like I've done, I've tried at least some small issue that I don't care too much. It's not, of course, what you are going to typically use in a day-to-day life. So what you want to do is to be able to do that inside a Slurm job. Of course, if you want to use that on your laptop, then you can use it a bit like this. But typically what we are going to do is to use that on a Slurm job. So, okay. So here is an example how to do that, a Slurm submissions on the method 3. So you first have to load your module, obviously. So module load DMTCP, load the version of Python. It's not that important, but you need, of course, to load the versions of Python. And then you run first your coordinator, and then you launch your program. Although I'll override an interval here, which is very important. Let's say after how much time you want to have a checkpoint. So in this case, you have a checkpoint every 30 seconds. Minus RRM is that so that you have a nice interplay with the scheduler, and we'll see that in a couple of seconds. And then you have Python, and you have those weird stuff. It's just to avoid with some very specific file open on the method 3, and that otherwise it will kill, will make it impossible basically to run DMTCP in the method 3. So that's a trick which is completely the method 3 specific, might not, we might need the same on NIC5 when we survive, I guess, because that's related to the C group features on the cluster. C group are not available on all, I mean, are not activated on all clusters, so that actually depends on that. So let's do that. Oh, what I did. So here I'm going to try to kill the buffering completely. So I'm doing this std buff -0 to everything, which is not that much important. Then I'm going to submit the file slurm_dmtcp.sub. So I'm running it already. I'm going to print the watch. It's running, and then I'm going to present it to you. So I submitted slurm_dmtcp.sub. And that's completely exactly the same file that you've seen on the screen. Loading the DMTCP, this line to launch the coordinator, and then this file to launch the program itself. Okay, and I need to check where I put the output. So the output is in the file called res. So I'm going to print what is inside the output, the -f of this file res. That you see the output printed on the screen. And there is every second, of course, one new number. So what's going to happen, obviously, I put a wall time again of 2 or 3 minutes. So obviously, I'm going to eat that wall time. My job is going to be killed. And then I will need to restart my job. So I'm going to wait that. And that's again going to take 1 to 2 minutes. I see there is a question, yes, on srun command for -n1 and y, I guess the overcommit, but Damien has answered it already. Ah, no, it's on the watch command. Is it the watch or srun? There is the two at least. Yeah. For the watch, it's really so that this command is refresh. I mean, it's run every second. It's printed what is the output of that command every second. So you can see that every second here, the timing is updating by 1 second. And the time here as well. So I still have to wait a bit. I don't remember if I put 2 or 3 minutes in that case for the whole time, but it will be killed any second. Okay, looks like I have 2 minutes. Well, I can already present anyway the next step. Yes. So the next step is to restart the program. When actually DMTCP, and I can already probably show that at the cluster, but I will do it after. DMTCP will automatically create a file which is called DMTCP restart script.sh. And that is the script that you need to run in order to restart the program. So that's what we are going to run. So you have another bash script that's going to run srun overcommit to basically redo the coordinator part of the DMTCP. It's technical, it doesn't matter too much. And what we are doing, we're going to rerun that script, DMTCP restart script.sh. And what is interesting in that script, and that's related to the -rarm of the previous file, this script will actually resubmit itself automatically because it knows that there is a scheduler. So when you are at this stage, you know that your program is going to end. It might take 5 submissions, 10 submissions. It doesn't matter. Your program will arrive to an end. So you see here that I hit finally my wall time, so it's killed. We kill here, and now I can submit the second script, which I call it restart. Okay, here I have 2 now. And now basically this script is going to run again. I'm not going to show everything, but that's basically what's going to happen, and then it's going to restart from 94. Okay. So this brings me to my conclusions. Basically, the idea of this lecture, it tells you to never discard your change, to be always able to restart from the beginning. So we have seen 2 main ideas, basically. The first one is to save after each iteration, which is the typical stuff that come to developers. The second one is to save when you have a signal. The second thing, which is of course useful for you, is to add those features to be able to have a requeuing completely automatically, so that you don't have to monitor your job actively. You know that if there is this automatic requeue, the fact that you hit the wall time or not are not important. If you hit the wall time, your job will be resubmitted. You will have to wait. You will lose a bit of time, 2 minutes of waiting time, or you might wait more simply because you need, of course, your job to be rescheduled. But basically, you know that your job will finish at some point, and that you will have the full result, whatever the wall time is, and that's of course very important. And then one trick, which is, I guess, quite important, is this open mode equal append, so that your log file have the full information for your full job and not for the full one Slurm submissions. Okay, so that's it for today. I don't see any additional questions on the chat, so we'll keep the chat open for probably 10 minutes as usual. So if you still have questions, don't hesitate to ask them on the chat, and then we'll answer them. Don't forget to have a sign for your certificate of participation if you need one. And then there will be also a survey that I guess Damien is actually activating right now about these lectures, or if it was useful for you, if I was easy to understand, and so on and so on. So don't hesitate to fill that survey as well. So thanks a lot.